So thank you, Professor Sol, and thank you very much for inviting me here, and thank you for being here. I see we've got quite a number of people on Zoom. Xiaoyu was a visiting faculty member with me last fall and invited me to give this lecture. And he initially said it was the Ardaman Lecture, and then he said it was the Ardaman-Wissa Lecture. And the more I sat down and thought about what I would say, I realized I really needed to think very hard about my own relationship with Anwar Wissa. And assuming this thing clicks forward, which it doesn't. How do I move forward, guys? One of these. There we go. We're in business. So I knew Anwar Wissa. I didn't know him especially well. He was a regular visitor to MIT when I was a student. So this takes us back a few years, I have to admit. And I realized the last time I saw Anwar actually was at a gathering of MIT alums in Florida, in West Palm Beach. See the folks here on the chair. For those of you who don't know Anwar, he's this fella here. Can we turn the lights down in the room? This is Anwar. He spent the early part of his career at MIT as a faculty member and moved down to Florida and became the head of Ardaman Associates sometime in the 1970s, or David Carrier and I are apparently about timelines mismatched somewhere. Anwar was also closely connected with Nadine Fullerheim, another MIT graduate who eventually also took over Ardaman more than 10 years ago. And both of these fellows were connected to this fellow here, Chuck Ladd. So if you don't know these people, these are the background people to this story, if you like. So what is it that Anwar has done to influence my career? Well, he did a number of seminal pieces of research and geotechnical engineering, which influenced our practice in lots of different areas. And I just wanted to sort of illustrate this before we get started. So I just thought I'd mention to start with, perhaps the best known paper he ever wrote was the design of a constant rate strain consolidometer device. And it's a paper co-authored with another well-known MIT faculty member who's in that photo, John Christian, who developed the theory along. And what's interesting to me about this paper, of course, is that the CRS device is universally used today. In fact, you would say constant rate of strain consolidation is the normal way we do testing. It has superseded incremental load odometer tests in many ways, or is used alongside it. It's a much faster test. But what's really intriguing, if you cast your mind back to 1971, and I can vaguely remember that, there were no computers, no personal computers, there was no computerized control. So this whole system was driven mechanically, and it was really a very elaborate design to be able to make this thing work. But the CRS has gone on to have this enormous impact everywhere. It has enormous impact in the sort of work I do on parameter selection and so forth. So this is a piece of work very much attributed to Anwar. The second picture I've got here is a picture of undrained strengths or undrained strength ratios, which should be familiar to any of you who work with clays. This is seminal work, largely originating with Chuck Ladd and his work on embankments on soft ground, going back to the 1960s onwards. And you'll see this particular paper shows some data from a joint project between Weisa and Ladd on the Connecticut Valley Varva clays, which are amongst the most strongly anisotropic of the clays that have ever been tested. So that work on clay behavior informs a lot of what we understand about clays today. The third thing that Anwar was involved in was field testing. He was involved in the original PISA probe development, which predates what we call PISA cone. In fact, some of the earliest PISA cone development was done at MIT following Anwar's work. And it particularly informed one key individual in my life, which is Mohsen Bali, who was my thesis supervisor. And when I was a student at MIT, we spent a lot of time looking at and analyzing PISA cones and how PISA cone could be interpreted when you push it on clays. So the PISA cone has had a lasting influence, and you'll see how this comes into today's story. And finally, once Anwar moved down to Florida, he became heavily involved in tailings, tailing waste, particularly for the phosphates industry. He produced a series of papers through the 1980s for an institute called the Florida Institute of Phosphate Research, which is a seminal set of papers on all aspects of phosphate tailing materials, dam design, dam management, and so on. It's a series of papers that went on, I think, until the early 1990s. And that ties into some recent things that have been happening in the tailings. So all four of these pieces of work were in my mind when I thought about presenting to you today. And I tried to think of how to tell you a story which integrates all these pieces. So hopefully you'll see if I accomplish this or not. So I'm going to talk about two topics. I want to talk about stability, and I want to talk about it in the context of tailings. And this is largely motivated by an extraordinary failure that occurred in Brazil in January 2019, which involved what is very visually, obviously, is a spontaneous liquefaction. And I want to show you something about liquefaction, what we understand of the soil mechanics of liquefaction, at least. I want to show you the challenge of interpreting liquefaction susceptibility in a tailings dam. And then I want to show you what we've done, which is in fact a much simpler approach. We've ultimately resorted to doing simplified stability analyses to make assessments. And we've found some serious limitations on the methods that continue to be used in practice. So that's one of the things I really do want to identify. The second topic is dealing with consolidation and creep of clays. This, of course, has huge impacts on tailings, which settle under their self-weight. But I want to show you how we have attempted to resolve a very long-standing dilemma associated with the way you scale consolidation and creep. And you'll see this revolves around a mathematical construct, which we refer to as a viscoplastic evolution law. So there's a little bit of math to explain this. You'll see how we've taken that idea, implanted it in the soil model, and then I want to show you some examples fairly briefly at the end of us using this. So the first thing I want to show you is the picture of the Brumadinho tailings dam failure, sometimes called Feijão. You can see in the top figure, you can probably, how many in this room have actually seen the video of this failure? You can see this on YouTube. It is an extraordinary video. I've just taken two still photos of it. One where you can see, in fact, movement coming out of the toe and the back scarp, and then one taken 10 seconds later, and you can see this entire mass is collapsing and flowing as a, what I suppose you would call a particle-laden fluid. It's completely fluidized throughout the entire soil mass. The soil mass here is up to 100, better part of 100 meters high. So it's an extraordinary failure. And of course, a tragic failure too. More than 260 lives were lost in this failure. It crashed downstream many, many miles. It was storing iron ore tailings. So this entire dam structure was storing iron ore tailings. 12 million cubic meters of iron ore tailings were released. It's very hard to estimate exactly the costs of this thing. There's been one settlement publicized, which was at about $7 billion of compensation. But this is sort of the tip of the iceberg. There are several other very large multi-billion-dollar settlements still to take place. Now, what makes this very interesting? Well, first of all, we can see the failure. We now see people have talked about spontaneous liquefaction, but to my knowledge, it's the first time anyone's actually videoed it to a point where you can actually see it and observe and understand what was going on. This occurred 4 years after another failure in Brazil, not so far away, called Fundão or Mariana. And that was in 2015. And you can imagine after that earlier failure, which also caused a lot of environmental hazard, loss of life and so on, there's been a huge review of the safety of tailings dams in Brazil. The Brazilian government immediately banned this form of construction, this upstream form of construction. Now, I had nothing to do with any of this, I should add, at least at the outset. For me, what got me involved was, sorry, I can't see the slides if you do that. What got me involved was the fact that there was an expert panel that was brought down to Brazil to investigate this failure. And they did a study and tried to find out the causes of the failure. When they finally completed their report in December 2019, they made the entire report public, together with all of the supporting data on the construction history, the internal monitoring, and everything. So there's an extraordinary data set there available for me and everybody else to study and understand this particular dam. So this was really an opportunity for me to try and understand something about this problem. Now, before we embark on some serious technical things, I want to point out that two major tailings failures with major loss of life in similar structures would be unusual. But if you actually look, over the last 10 years or so, we've had 37 major tailings dam failures, and I know that number is now out of date by a year or two. 11 of the 37 have caused fatalities on top of this, all around the world. If you were to ask what has caused the failures, by and large, in all but this one, people have been able to attribute a hydromechanical cause. In other words, changing flow conditions somehow have been related to the failure. In this case, the construction was finished in 2016. Nothing was occurring. The monitoring of the water pressures showed very little change in water pressures anywhere inside the structure. So it's not obviously a hydromechanically caused failure. So this raises a very interesting question. But as you can see from this, the risk here is completely unacceptably high. We probably have the order of a few thousand tailings dams out there in active construction, and perhaps twice or three times that number which are capped and closed. And you could see that we're dealing with fatality numbers that these things shouldn't be occurring anything like 37 times in 10 years, 4 times a year. It just shouldn't be happening. This is a completely unacceptable state of affairs. So the whole practice of mine disposal has been raised here. And in August 2020, you'll see there's a global industry standard on tailings management. This is a document. It's not a regulatory document. It's a document put out by 3 very interesting groups of people. It's put out by the mining industry, which is ICMM, is a trade group representing the mining industry. It's put out by the UN Environmental Programme, and it's put out by PRI, which is a responsible investing group. These are the investors in the mining industry. So these people are saying something needs to be done to improve management of tailings. And that, of course, starts with being damn sure we have stability of tailings at all times. So this is a very critical issue, I think. Now, from a soil mechanics perspective, the story of tailings has to start with the way they're constructed. And there are you can distinguish 3 different types of construction sequence according to where you store the dumped tailing mass and the dam structure itself. And in those figures, you see the dam structure in the dark brown, and you'll recognize that upstream dams are built upwards, progressing upstream, with a very small footprint of the dam structure, and the tailings that may in fact be deposited, and you may be building on recent tailings. So this is the upstream construction, and you can contrast it with the downstream, and you can see how the footprint varies according to the amount of dam relative to the structure you're storing. Our interest, of course, is primarily in what's stored and what's happening behind this dam structure. In many parts of the world, they segregate the materials. This is a hydraulic fill structure. Most of these structures are hydraulic fill, and they segregate by particle size. In some parts of the world, you'll come across a device called a hydrocyclone, which takes the raw mixture of particles in the fluid bed and separates them by size. Whether that is done through a hydrocyclone or other means, what you generally end up with is a construction where the largest particles are deposited closest to where you're currently depositing. You may have what are called beaches, which are essentially sand flowing downhill and depositing and segregating down the hill, so that you have particle sizes with more fines progressing away from where the point of discharge is. And if you get far enough, you get to the pool structure, which people call a decant pool, which is where you get slimes depositing out of solutions. This is where you would expect very low permeability silts and clays to arise in the decant pond. And the structure of these things vary according to the materials you're mining, the type of mine material. If you're interested in these things, there is a very useful textbook, and I would recommend it to you. It's a book by Jeff Blight, who's a former professor at the University of Witwatersrand in South Africa. And it gives you an overview of the practice, the geotechnics related to these structures. Very useful overview. There are other books too, but this is a particularly useful guide, published, I think, in 2010. I want to move quickly to the issue of stability. And in order to do that, I've got a little cartoon here. Please bear with me, it's not intended to be a terribly realistic structure. What I've drawn is a slope in the soil. I'm imagining that we're looking at a potential failure plane, that's the dotted black line. I've chosen to focus on one point on this, which is the little red dot. Because it sits beneath the slope, it's got shear stresses, so it's got shear stress tau acting on it. And somewhere in this slope, we have a water table, and I've represented that, and you'll recognize there is some kind of seepage field inside the structure. And so the question is, what causes failure or instabilities of tailings? Well, as you would imagine, if you start building on the upstream side, you're adding stress. You're adding vertical stress, you're adding shear stress. I've sort of offset this point one just to make the point that you could be building fairly far away from the failure plane, and you would still be adding shear stress. And then on the little right figure, you'll see I've got the vertical effective stress, the tower, and a little red point. And notionally, you can see if I build over here, I'm likely not increasing the vertical stress here, but I'm certainly increasing the level of shear stress. So my stress path is vertically upwards, directed towards the dotted line there, which is my more Coulomb failure envelope. I can create many other scenarios telling me what might happen from that initial red dot, if you like, the initial equilibrium state. One of them says that the water table increases. If the water table increases, you can imagine you saturate the soil above perhaps in the initial capillary zone, so you're adding dead weight, you're adding potential energy to the system, so you're increasing total stress, you're changing the core pressures, and again, you're changing shear stresses. The path that you follow here in this space is likely one where you're decreasing the effective vertical stress, and you're not changing the shear stress very much in this path. So the path is directed to the left. And you can create other scenarios. There's another scenario. The scenario is I excavate the toe of a slope, and I can play this thing through, and you'll realize there's a third path. There are multiple paths. All of these paths are essentially increasing the ratio of the shear stress to the effective stress. And I think all soil mechanicians know that's not a good direction to go when you're looking at shear strength for soils. All of this is sort of predicated on us looking at the drained behavior. Everything performs in a drained fashion. All these stress changes occur sufficiently slow that drain conditions apply. Of course, I could build zone 1 or excavate zone 3 relatively quickly, and therefore you could trigger things occurring at a much faster rate. You could achieve producing changes very quickly. You can get the undrained behavior. Undrained behavior effectively says that there's no migration of water within the soil skeleton relative to the skeleton itself over the time frame of loading. In principle, if the soil is saturated, you will get a unique response, a unique undrained response for all those cases, in principle. And I've sketched the undrained effective stress path. And you can see on this effective stress path, strange things happen. You'll realize that the undrained effective stress path may have a strength, a peak shear, which is not coincident with the more Coulomb failure envelope. It may involve a softening, so that I have a state where the shear stress is in fact lower than the initial stress state, so I can have an unstable condition. And you may even get stabilization in some situations where dilation seems to occur at larger strengths. We kind of know this stuff from soil mechanics. I want to add a few more colors to this relative to our particular situation. So the point I'm trying to make is if things were undrained, you would have a unique response, at least if everything were isotropic. Now, what is the challenge for us in tailings? Well, the challenge, as I've laid out, is that we segregate our materials so we have different parts of our tailings structure with different particle characteristics. And I just illustrated for you the case of the Feijão failure that we started with in the video. And you'll see in the three colors are three characteristic grain size distributions. The slime material in the deckhand pond to the far right has a clay content somewhere in excess of 50%. I should say that this is very low plasticity fines before we go further. You'll see the coarse material may have as little as perhaps 10 or 20% silt fraction and is likely to be free draining. And when you put more and more fines in there, you will reduce the permeability. You may also have some influence on the shear strength, and that's the fines material. So these are three characteristic curves. I ignored all the scatter just to make the point. There are three very distinct materials that we will talk about. The other thing I put on this figure, just to remind us, is that tailings are not the usual materials we come across in conventional soil mechanics. They are the waste product of the mining industry. So this is coming from an ore deposit called the BIF, which is a banding iron formation, the sedimentary rock formation. And what's extraordinary, if you look at the distribution of minerals in this material, you will discover that there's an extraordinary amount of iron in the waste stream. It's almost inconceivable how much there is. You'll see there's hematite, goethite, magnetite, all iron oxides, and you'll see that the specific gravity of the material stored here is much, much higher than you would come across in soils. We generally think of specific gravity in a very bounded number between quartz and molten between 2.65 and 2.8. Here, the numbers are anything up to almost 5. Huge amount of iron ore present in the waste material, which of course adds to the driving force, the potential energy of the system, this unit weight that you're dealing with. So we've got an unusual material with a very high GSVT. Turning back to our stability problem, a late colleague Chuck Ladd, in his Terzaghi lecture in 1991, identified different classes of stability problem that one could analyze. I don't want to repeat all that's on this slide. I just want to draw your attention to cases 2 and 3. Ladd says that in many slope problems, the stability condition that is most critical to you may be a drained or long-term stability problem, where you identify the full consolidation state with respect to the applied stresses, and the strength that you're dealing with is SD, it's the drained shear strength, tau m being the shear stress you have in the equilibrium condition. The partially drained state, this is what he uses frequently in stage construction. And in stage construction, he argues that you should evaluate stability against the undrained strength that is available to you at the time when you want to consider the loading event. So this is the consolidated undrained case, and you can see the difference here is that you reference this to the SU or undrained strength value. So this is the logic of how strength or stability is considered in most geotechnical problems. If I put this into a very simple stress path, you can see, relative to what I was telling you of the tailings, you can see that the green path is the path for loading. The case 1 I was identifying. The red would be the undrained response to that same action. And you can see the green and the red dots represent the undrained strength and the drained strength condition of the material. And if you apply factors of safety or simple judgments on this, you'll realize that the factor of safety in the drained case, SD divided by tau m, is nothing other than the ratio of tan phi at the more Coulomb envelope divided by tan phi m. I just put in there that people often assume the cohesion does the same, and the undrained strength is SU divided by tau m. I just wanted to remind you of this situation. All right, so let's go back. What we'd like to do is say, what do we expect undrained strengths to look like for our materials? Well, in the case of clays, and here, when I say clays, think slimes. For the case of slimes, I would argue the conditions are nearly one-dimensional sedimentation in ponds. Therefore, they look much like the conditions of all other sedimentary clays, for which my colleague Chuck Ladd has an enormous data set of the properties of clays. And here is a summary from his work of undrained strength ratios. The figure on the left shows you properties of many, many normally consolidated clays. The figure on the right shows you the effect of the over-consolidation ratio. The point of this figure is to illustrate for you that, in fact, the undrained strength of clays we generally consider only as a function of the direction of shearing. And on the left-hand figure, you can tell the direction of shearing by the different colored symbols. The symbols in blue are indicating triaxial compression strengths. The symbols in green are simple shear, pretty much what I showed you in the slope, and the red are triaxial extension. The fact that these are not all the same tells you that clays are anisotropic. So we have anisotropy emerging in the undrained strength of soft clays, especially normally consolidated clays. The figure on the right shows you the other parameter of interest to us is the over-consolidation ratio. In the case of tailings and tailings ponds, we're looking at the left figure. there is no OCR effect. We're building the tailings up continuously. So this is the case with normal consolidation, self-weight consolidation. I've never personally found this a very convincing figure on the left because plasticity index doesn't really reveal terribly much about anisotropy, all these trends. But what you can see immediately in the figure is that the ungrained strength ratio is relatively well bounded. And in general, the simple shear mode generally lies between the other two. So it represents a sort of average condition and is frequently used in design of slopes. So simple shear strength is widely used. To make matters just a bit more entertaining, I should point out that's what phosphate tailings look like. They're way off this figure. They have plasticity indices of hundreds of %, and you'll notice that the extension strength is higher than the compression strength is higher than the simple shear. So just to prove to you, we can find materials that don't fit everything that. But in the case of Feijão, we know the plasticity somewhere between 10 and 20%, and we can make a pretty good estimator of the ungrained strength ratio of slimes at the Feijão site. There are no data. There were no measurements of the slimes property of the Feijão failure anyway. So everything is focused on the other materials. So let's turn our attention to them. When you start discussing ungrained strength of sands, you need a good data set to understand how it differs to clays. And I picked a data set here from Ishihara, who's one of the world's great experts in soil testing. And it's from a different site. It's not from the tailings dam. It's from the Jamuna River, which is a river in Bangladesh. And it's from a site where they were having flow instabilities during construction of a bund for a bridge. So it's a site which had experienced a lot of flow failures. So they studied behavior rather carefully. What you see in the figure is a summary of a series of triaxial tests run on Jamuna River sand. And you'll see the stress cards on the left and the stress strain curve on the right. And you'll realize I picked a data set with one level of confining stress, one amount of fines, and the only thing that's varying with different colors here is the density, the void ratio at the time of shearing, E0 value. And you'll see the void ratio going between 0.87 and 0.80, denser conditions in green and much looser in purple. And what do you see? Well, you can see that the stress strain curves differ hugely. You go from things that are stable and hardening, producing very high levels of shear resistance, to things that soften and are rather brittle and reduce resistance with ungrained shearing. All of these data we measure today using strain control. So we have ungrained conditions, meaning constant volume, and we drive them at a constant rate of strain. So everything else is held here, if you like, at constant velocity, constant strain rate. But you can see the only thing that collapses is the loosest state. The other thing that captures the mind of all geotechnical people should be the peak strengths and the large strain condition. And you'll see the large strain condition doing what we've been learned all through class in Casa Grande, reaching a condition of constant shear resistance or critical state condition. So the critical state has absorbed much of the energy of geotechnical engineers looking at flow failures. They argue this is the steady state condition that soils should reach when you shear it. This is data on the steady state for another sand in Japan, the Toyura sand, one of the best tested materials in the world. And what you can see is the void ratio at critical state or large strain conditions plotted against the level of stress. You will see a bunch of points with the open circles or ungrained shear, meaning we did what you just saw in the previous figure, and we picked up that end state. And the other figures with the black dots are drain shear. And you can see that we can approach a critical state from below. When we dilate, we increase the volume, and you can approach a critical state from above where things collapse. But you can see all of those points lie on a locus that appears very well defined. So the steady state appears to be a very useful reference condition for understanding the large strain condition in drain or undrained shear sands. And this has been used for a long time as a basis for trying to diagnose how sands will behave. And this dates back primarily to the work of Bean and Jeffries in the 1980s. They have a thing called a state parameter. the state parameter is just an index of the void ratio of where you're currently at relative to the void ratio at the critical state at the same stress level. So what you're seeing in the figure, the two blue dots represent two possible states. The red is the critical state or steady state line. If you're above the steady state parameter is greater than zero. If you're below it, it's less than zero. So things dilate with the state parameter less than zero and potentially contract greater than zero. This is very well known. I should point out that these locuses of critical state are actually quite hard to determine. In fact, this is a very big practical concern here. This is the actual data on critical state for the same material here, shown at a different scale. Rather than plotting a linear scale over a small range of stress, I stretch the stress scale, putting it on a log scale, and you'll realize that the data points here fall on a nonlinear locus. I've shown you what would happen if I started with, say, psi equals 0.05, similar point here, and I ran undrained shear, I would collapse. I would have no residual strength at all, because you can see I reach effectively zero stress at that state. So how do we use this in Feijão? The investigations of Feijão focus very heavily on determining state parameters. Here, for example, are data on the Feijão sands. These are triaxial shear. I tried again to find a compatible data set to make the point I wanted to make, which is, you can see I've got, these are all materials with a high fines content, 70+%. So this is the fines material. And there is one data point here, which is marked in, what color is it? I can't even see. There's one coarse point. You can see that as we have changing void ratio, we go from materials that dilate, we have very high undrained strength, to materials with an undrained strength which soften. And critically in Feijão, we have materials which can collapse almost completely, either the coarse fraction or the fine fraction. So we have material which we know is prone to complete liquefaction here. If you ask, how well do we know the steady state for the Feijão material? The answer is, as well as this figure suggests. You can see these are all the data available for a blended mix of the tailings, and you'll see the endpoints are all marked in black, and you'll realize that drawing a straight line through those points isn't going to be so easy. Part of the problem is that as you change the fines content, you change the location of the steady state. This figure on the right is a figure we put together, separating out the steady state strength of the coarse material. That's the purple line. The green data are the stuff I showed you from the Jamuna Bridge in Bangladesh. You'll realize they're very similar. The red stuff is the data on the much higher fines fraction of the tailings. And you'll see there's an enormous offset between these steady state lines. The void ratio here is shown rather clearly. You'll appreciate that's directly an index of the state parameter. And you'll look at the scatter and you can appreciate that determining the state parameter within plus or minus 0.05 is going to be very difficult, and it's going to vary at different points according to the fines fraction. So this is really quite a challenge for us. Now comes the really interesting thing. Undrained strength is not just a factor of the void ratio, it depends on the prior stress history, in the same way it did for clays. Clays is the over-consolidation ratio. Here's an example showing you what happens when you start doing a drainage shear test, and then you switch off the drainage condition and you go into an undrained mode. The figure shows this is a simple shear mode. That's the little sketch on the top right. You can see the stress path and the stress strain behavior. And you'll see, first of all, the green line. The green line is what happens when we shear very slowly this material under drained conditions. And you'll realize that we can traverse all the way up to a strength envelope, more Coulomb envelope. All the other colors on the figure are where we convert to undrained shearing at some point. So we follow the path, then we stop drainage occurring, and we do undrained shearing. So you'll see this is the undrained strength. If we start from here, the undrained strength, we start from here, and so on. Delta tau is the amount of shear stress available to you in undrained shearing from any starting point. So you can see the delta tau value is the increment of triggering shear stress that would be of interest to you based on some initial drain condition. And hopefully you can see the very obvious feature, which is you go from the blue line up to the yellow line, that delta tau value gets smaller and smaller with the level of the shear stress. And the level of the shear stress would be reflective of the stress conditions in the slope. The higher the slope angle, the further you would be up on this line here. So undrained conditions are going to be very tricky if what we're interested in is the triggering condition, because the delta tau varies with the initial level of shear stress. And we can say that when we're below a certain level, things are stable. When we exceed that, we're going to get an unstable response whenever we have a loose material with a state parameter substantially larger than 0. So it's really quite a challenging problem. Undrained shear of sands essentially is going to be a latent instability. We can observe perfectly stable stress states, and we've got to ask ourselves how much triggering we can tolerate before we get the collapse that produces the liquefaction. So it's a very difficult problem. Finally, I want to point out something which nobody that I've seen so far has appreciated, which is that because of the way we form tailings, they have a material structure. They have anisotropy. So we form the sand on an incline. It's like we create our own beach by letting particles roll down the slope. That means we have material anisotropy associated with that direction, different to the direction of stresses. It is very hard for us to assess anisotropy with conventional devices. You can't measure it in a traction cell because the directions of stresses and particle orientations are in the same direction. But you can measure it in a device called a hollow cylinder shear device. And this is a set of results from Georgiano, MTU in Athens, on another sand, I should point out. What you'll see in this figure, stress path, stress strain behavior, same material, same initial conditions, same starting point. What we're doing is shearing with the principal stress oriented at different angles, alpha to the vertical. So alpha equals 0 is a compression. As you go to higher and higher alpha, you have a higher rotation in stresses. The stress strain curves are completely different, as you can see. You'll see that the peak strength, the undrained strength, varies significantly with the direction of shearing. Now cast your mind back to my original cartoon. Our starting point is perhaps some point on the purple curve. And then when we try and rotate stresses or increase the rotation between tau and sigma v, we're crossing along here, we're crossing horizontal. And therefore we can simply create failure by rotating principal stresses, which is an extraordinary thing that is very likely at the heart of this problem. Georgiano does this. She starts out with a series of stresses, and then all she does is run undrained shearing, where she rotates the principal stresses. And the stress paths here show how far she gets. So she starts at 5 degrees, she fails at 12. So as you rotate principal stresses in undrained conditions, you trigger instabilities due to material anisotropy. So this is an extraordinarily difficult piece of behavior also. Okay, having set this problem up, let's rewind and then ask ourselves how to solve it. This is the history of the Feijão Dam. You can see many phases of construction. In an upstream construction, each one of those dam raises involves re-permitting and demonstrating safety in the design. So each stage has a design safety. We know the construction history, and you can see the instrumentation to monitor inside the structure. We also know roughly where the pond is located, so we know where the deckhand pond is, we know where to expect slimes. So we have a lot of background information to let us construct the whole history. Most of the data on stratigraphy really come about by a series of piezocone tests that were run after the failure at Funda, so in the post-2015 era. That's what you see mainly in this figure. And the focus I'm about to show you is on section 3.3, which is where the observed failure first appears. So here's a piezocone test. It's critically one right in the middle of the slope and right in the middle of the failure zone. The cone resistance is shown on the left, friction ratio of core pressure. You'll see there's an overlay of interpretation on this figure, which you can read about in the paper we wrote. But just to be very simple about this, we have a primary classification here. We assert that when there are no excess pore pressures, the Pisa cone is measuring drain penetration conditions and is likely associated with coarse tailings. When there is excess pore pressure, we expect it's going to be slimes. The higher excess pore pressures will be associated with slimes. That accords with the color scheme you can see on the background on the left. This is the expert's interpretation of stratigraphy, and you can see the color schemes where it's brown, that's the tailings material coarse or fine, and the green is the finer tailings. They don't distinguish slimes. But in my mind, this is slimes. We have very high excess pore pressures, similar to what we would find if we pushed a Pisa cone with clay. So we think this is the undrained response of the material. So our primary discrimination is to figure out drain from undrained behavior. The question is how to determine parameters that we could use to be able to figure out or interpret the failure. The challenge, you'll see, comes down to something quite simple because we don't have a huge amount of this data. Most reliable information on calibrating the cone resistance of sand to properties, the cone resistance to the properties of sand come about from work done back in the 1970s and 80s. They ran controlled experiments in what we call very large calibration chambers. In fact, as I recall, Mike's nodding his head, as I recall, Professor Schmertman had one here at the University of Florida. Bottom structures lab. There we go. So, calibration chambers, you create essentially a large vat of sand at a controlled stress relative density, and you push a penetrometer, measure the penetration resistance, and correlate from there. Huge multinational effort to make these correlations come about. And if you go back in time, the plot I'm most familiar with comes from a textbook by Renato Lancialotta in the early 1980s. It looks like this. And what you'll see is the cone resistance correlated against relative density. And this has all been updated. I'm sure if I asked Paul Main to show you this plot, he could show it with a huge amount of data on it. The story really hasn't changed. What you see in the figure is there is a correlation between the cone resistance and relative density. It's not a very precise correlation. You can see that for a given cone resistance, you're going to be hard pushed to get relative density plus or minus 10%, which I think is a useful number. There's a lot of data supporting this. Do we have cone tests supporting this in the tailings from Feijão? No. So we then have to assert that this is realistic for the Feijão material, which is perhaps an assumption. For the tests in clays, Pisa cones in clay, we know that if we push a cone in a low permeability material undrained, the undrained strength is proportional to the net cone resistance. Net cone resistance being the measured tip resistance minus the total vertical stress of the depth. And the correlation coefficient is a cone resistance factor, NK. Obviously, given that SU of clays varies with direction shearing, it's anisotropic and with OCR, you have to make some inference as to which undrained strength you wish to obtain. In the case of Feijão, we're interested in the simple shear strength. I asserted to you, we know the undrained strength ratio of that, therefore we can back figure NK. How does this work out? Well, if you look at global data sets, NK varies. NK is not a universal constant because the more brittle the material is, the stiffness of it pre-peak all affects the tip resistance. So there's not a universal value of NK. You would generally do site-specific correlations. This is what is shown in this figure from some work at NGI. NK 15 plus or minus 5. We found at Feijão, NK would be 10 to match the data. So taking these pieces of information on board, you can revisit what we've said on this figure. You'll see that wherever we have green slots, we're saying this is slimes. The red line is essentially saying we know the undrained strength ratio, we know the cone factor, and this is our fit. And you'll see that we're correctly getting the right order of the cone factor. The fact that the cone factor is lower than we might expect, having a lower NK, may suggest something else that no one measured, which is the clay here may still be consolidated, maybe under consolidated. In the draining areas, you can see the overlay, the relative density correlations. And you can now appreciate that versus depth, there's a huge scatter in relative density. There are many places where the relative density is less than 30%, but interpreting relative density better than plus or minus 10% is difficult, getting the state parameter even harder. So we decided not to trouble ourselves too much with that level of detail. What we did instead was we said, let's put on the maximum amount of fine material in the space. So the yellow layers on the right represent where we're very sure we have a coarse material with few fines. The red material is where we think most likely we have some slimes. And the green is where we think we could be in that fine fraction from the deposition. And we went around all the piezo cones looking at things this way. The consequence is you come up with uncertain stratigraphy. And you can see in this figure, I've got 6 examples of an uncertain stratigraphy, color-coded the same way. So you can see precisely where we think the slimes are, intermediate layers, and so on. The top one is probably our preferred or best estimate profile. We took it all the way down to just coarse material, just uniform tables. By the way, the water table is also shown here. This is a phreatic line, which hardly varied prior to the table. So we created these uncertain stratigraphy profiles and then asked ourselves, well, what properties do we want to assign for stability analysis? The water pressures, I will spare you, but the water pressures we fit with a very simple model. The different layers, of course, have different hydraulic conductivity, so that they affect the results. The model fits rather well the measured data, I think, is the method. Something very interesting they did here, they measured water pressures from the dissipation of piezo cones. So they also have water pressures at the time the piezo cones were taken, which is also a useful piece of data. So now we come to the stability. What method do we apply for this? And if you look out there in the literature today, there are essentially 3 styles of doing stability analysis that you should be aware of. The first one is limit equilibrium. And I would challenge anybody in soil mechanics not to know limit equilibrium. Limit equilibrium should be extremely familiar to you. In the limit equilibrium method, you assume you know where the failure mechanism is. You, with some assigned properties, you can work out factors of safety, and then you search for the worst factor of safety for the search. So the search mechanism is extremely critical. And in a structure such as the tailings dam, it's far from obvious where the failure mechanism would be when you make this in design. So limit equilibrium is a real challenge given the uncertainty in stratigraphy. The second one is what's becoming increasingly familiar. This is using deformation-based finite elements. And deformation-based finite elements, you can adopt 2 strategies. The one in red is essentially to build up the dam from scratch and work out the equilibrium conditions that you have. And then in that situation, how would you investigate stability? You would try and trigger a failure. You would associate, you would look for triggering of a failure. So that would be using a general soil model. There's another way you can use this, is you can get to that state and do what's called a strength reduction. These days, a lot of people use a program called Plaxis, which has a thing called a C-phi or a phi-C reduction. It just reduces the strength until you cause a failure of equilibrium. So strength reduction is also possible using conventional finite elements. The method you're going to hear from me is the third one, the limit analysis. Limit analyses are still not established in geotechnical engineering for computation, regular computation of stability, which is kind of absurd. They've been around for quite a while. There's a wonderful paper by Scott Sloan in his ranking lecture in 2013. We all use these methods. We just don't know it. Bearing capacity factors, earth pressures, all come about from upper and lower bound plasticity theorems. They all assume rigid plasticity. So that's the same as the limit equilibrium method. Historically, they were solved by quite complex methods, things like the method of characteristics. But Sloan has changed that algorithm. He has now created a method of solving these using finite elements to discretize and then solving upper and lower bound problems. So it's a beautiful way to generalize the problem. This technique is really robust. It's a very powerful technique for design. The software to do this, the first commercial software has really only been out for about 5 or 6 years. So this is the one you're going to hear from me. Let me come back a little bit. Before I admit that we're going to use that software, what do I know about modeling the failure that I described to you in sand? The answer is we have constitutive models of sand that could, in fact, predict liquefaction. The one I'm thinking of particularly is a model that was generated by Juan Pastana in the 1990s. And it's based on a plasticity model, it's an elastoplastic model with a yield surface that is anisotropic. It can rotate and move, generate inherently evolving anisotropy. And it does this through this rather complex function here, which we call the yield function. I know that this will produce failures because the surface itself over here has a particular property which tells me that the internal elastoplastic modulus of the model will produce a failure. So I know this condition. In fact, I can illustrate it by just showing you the gradient of the surface, and the gradient, the FDP dash, drives the instability here. So I know that we can produce failure with an elastoplastic model resembling the liquefaction of the soil. We can check it out. In fact, working together with Giuseppe Buscanera about 10 years ago, we worked this out. We actually went through a calculation and we said, let's make sure that we can identify when we get liquefaction in this model. And to prove to you that I'm not talking total BS, this is the model, and you will see the model predicting collapse for various sands on the left. And if I zoom in on this figure, you will see the red is the collapse index, and the peak strengths here prior to collapse are predicted at this state here from this index. So we can actually predict when we're going to get collapse in this model, which is great, because now with this model, we can predict all those triggering conditions inside the tailings tank. Again, to show you that this is possible, these are simple shear tests. They're like the triggering tests that Pike did at Jamuna. And you'll see how the ungrained strength migrates across here, reflecting the slope angle that I have. So the pre-ungrained shear drain condition. And we can pick up from this the delta tau, the instability. So that experimental data is qualitatively fitted here in this model. So why don't we just use this model? Because it gets incredibly complex. It gets complex because the triggering position depends on the void ratio. So you can see how triggering is affected by varying the initial void ratio, that varied between 0.98 and 0.9. That triggering affects it, and as if that wasn't triggering enough, it's affected by the stress level, so the depth you're at. So we have this very complex triggering of the instability, which we could use if we knew the state of the soil everywhere inside the tailings tank. And more power, I know a number of researchers who are trying to do this, but it's like tracking down a needle in a haystack. So it's an extremely difficult thing to do, and I wish them luck. The model is there, and conceptually it's very useful. If you're interested in this work, we actually have applied it for simple liquefaction problems of a couple of slopes in this paper in 2012. So it's not that we haven't thought about the problem, it's just we've recognized the limitations on what we might be able to do. So what can we do? What we can do is really look at this whole issue of the factor of safety and make sure we understand what is an acceptable factor of safety using conventional strength reduction. In this figure, and I apologize, this one may take a minute or two to describe, the vertical axis here are the ratio of shear to normal effective stress in the triaxial mode of shearing. And this is the ratio of shear stress to normal effective stress in a simple shear mode. So we're combining the two shear modes. If I plot in this space, I can infer or plot a more Coulomb failure envelope as a circle. So you can see a circle of more Coulomb failure with a factor of safety of 1 is the red line. If I assume the factor of safety is 1.0 2.5, you get the yellow line, 1.5, the green line. For the Jamuna Bridge, we have triaxial and simple shear tests, triggering tests, and membrane tests with different conditions. You can put them on this figure. All of the solid dots in this figure are failure points measured in the tests. All of the open points are stable conditions. And hopefully you can see that things fail at a factor of safety of 1. In this brittle material, they can fail at 1.25. By 1.5, you're starting to breathe more easily. In other words, conventional assumptions on the factor of safety are perfectly credible ways of being sure that you're not triggering a liquefaction. But you need a large enough factor of safety. So the factor of safety can't be in the 1.2, 1.3 category, or you have problems. So this is what this data set shows us. So let's revisit Beijing. We are going to use these numerical limit analysis. We discretize them. And thanks to this technique, we can discretize the hell out of our problem. We can put little elements the size of even the smallest layers we have here. So layers which are the order of a meter thick, we can discretize quite successfully. And you'll see with many, I think the number we used was something like 500,000 elements here, we can discretize this mass. And having discretized it, we can feed in all of the strength properties to all the layers we want to input. We can feed all the water pressures to all the unit weights. And at that point, we can do a calculation of the factor of safety. And we can do it by a lower bound method, which is essentially statically admissible stress fields. For those of you who still think this is regular finite elements, if I do statically admissible stress fields, every line in this figure, every junction between each element is a stress discontinuity, not continuous stress. If I do upper bound analysis, we do kinematically admissible velocity field, and here we compute internal energy dissipation and external work. Every line between every element is a velocity discontinuity. So although this looks like conventional finite elements, it's not. It's two completely separate calculations. And to show you the outcome, here's the outcome for that first of the stratigraphies that we thought was applicable with the parameters I described to you. You'll see the top figure is the lower bound and the bottom figure the upper bound. We have looked at different ways of characterizing the failure mechanism. You can see that in the upper bound, we use what's called a plastic multiplier that figures out where we're actually at the failure state, and you'll see that forms a band. In the lower one, we look at the velocities, we look at how the whole thing is moving, and the arrows indicate for us where it's moving. What's important to understand is they're completely separate analyses, but they're showing us the same mechanism. You can see the same basal plane is occurring. It comes all the way down to the base of the slimes, to the laterite interface, and it drives down into the underlying soil, and it destroys the entire starter dam. So this is the triggering condition, we think, of a massive failure. Then look at the numbers, and you'll see the factor of safety varies between 1.12 and 1.188. That's the bounds on the collapse, assuming we are correct about stratigraphy, soil properties, water pressures, and so on. It's the bounds. And the bounds are quite narrow, so our uncertainty is quite small. So this is one result for one stratigraphy. We could play this, we've played it many times. We did this for 6 different stratigraphies, and I think they cover all the likely conditions we're going to see. We've also played with various soil properties and so on. You look at these, each of the profiles is a different profile, and then you look at the factor of safety numbers. One is the lower bound, one's the upper bound. You took the average plus or minus, and you can see they're all in the same range. So the factor of safety here is 1.1 plus or minus 1.2. It's nowhere in 1.5. So the stability of this dam against a massive failure is much lower than people clearly believed at the time they were doing everything else. So nobody should be permitted to build this thing up the way it was. So we go back and we ask ourselves, well, what did everyone know? And we can go through the auditing report in 2018, and we can go through the expert report. And you'll see all the lines on that figure, all the colored lines, the broken black lines and the red lines, or what were reported. And then you'll see how they were computed. These are conventional limit equilibrium methods. You will recognize them. They're using the Spencer method. Some use non-circular search, some use circular search. We didn't have the space to show all the stratigraphy assumptions, but they had a model of stratigraphy not dissimilar to ours, the properties and so on. In some cases, the stratigraphy, they assume saturated versus dry. There were various assumptions, but look at the factor of safety. You can see that by and large, they were producing factors of safety that they considered perfectly reasonable using various programs that exist now. But the factor of safety, the mechanisms, are nowhere the mechanism we're finding. So they're being misled. They've done a search, but they haven't found a critical mechanism, and they think they're in a much higher factor of safety. So they're being misled in this diagnosis, if nothing else. And you can ask yourself, what does this mean? Well, it means to me there are serious errors in LEM being applied for such a complex stratigraphy. That is very clear to me. It says that the external search methods used in most LEM programs are not robust enough. So there's something wrong with the search. It may raise questions about the properties and stratigraphy, but that, I think, is the heart of the problem. And I think the problem is we've been using these programs with little advancement for 40 years. And we've not questioned some of these things the way we should. But the new methodologies for stability analysis are very unambiguous and very clear. And that's the message I really want us to know. So let me just summarize this. It's a catastrophic liquefaction event. We know the fill is very brittle. We know it's likely to collapse. I've not described what happens when it does collapse, because it transits in 10 seconds to a fluid. It's very difficult to perform credible CU-type stability analysis because of the segregation of the materials and the complex modeling that's needed to characterize that. Stability by strength reduction really remains the essential design tool, so I think it's still the way we do business. It requires us to estimate the shear strength and the pore pressures, but that's nothing new for us. And these finite limit analyses are really a new capability. They're going to revolutionize how stability is done in geotechnical soon. I've just been saying that for 20 years, so soon. They don't require any external search. It's a very robust estimate of factor of safety because you do upper and lower bound and show the same mechanisms. And finally, it's clear that whatever was done at Feijão, they were overestimating factor of safety by and large, and therefore had unwarranted confidence in the stability of the design. Okay, I have no idea where I am for time. I'm sure I'm running way beyond the 1 hour. I know we started late. I've got a whole second part. I promise you I'll make this a whole lot shorter. I wanted to draw your attention to something completely different and try and pull out another way of doing research on an important problem. This is dealing with the problem of very large deformations occurring over very long time periods. And it's revealed by looking at another big project. This big project is the construction of the Kansai Airport in Osaka in Japan. This is an offshore airport. You can see it was also built by hydraulic filling methods. The fill methods are not terribly important to us in this case. You can see the runways are about 4 kilometers long, so you can work out the width of the runways, and you realize this is a massive structure. It was built by reclaiming the land in water depth somewhere between 18 and 20 meters, and it progressed from the first to the second phase to deeper water. What's of interest to us is that underneath this, we have a huge foundation problem. There are very deep compressible sediments underlying this airport. And as a result, the people managing the airport have to deal with very large ongoing settlements. There have been 5 meters settlements since the airport opened in 1994. The current settlement rate, the whole airport is something like 7 centimeters a year. And in order to protect the whole runway from typhoons, there is a big seawall all around this structure. So it's a very interesting dilemma they're in. How does this come about, and where is the soil mechanics of critical concern? This is a cartoon of the structure. What you need to understand is all those layers labeled MA and so on are layers of compressible material, clay-like materials, sandwiched between much more free-draining sandy materials. Each of the sublayers, the colored sublayers, is the order of 10 meters thick. So just keep that as a number in mind. You'll see settlement versus time reported from the Port and Harbour Research Institute. This is now a 10-year-old figure, but you'll see that the end of construction is the purple line. You'll see the upper layers of the soil, the Holocene sediments, which are under 10,000 years old. They all compress very quickly, and the compression is completed within the construction time frame because they were able to improve the ground by sand rates. So they accelerated consolidation. All of the deeper layers continue to compress. And this is where I got my 5 meters from. You can see these lower layers are continuing to deform over a very, very long time period. And therefore, we've got a very deep-seated source of movements driving the settlement of the runways in the airport. In soil mechanics, we treat all of these compressibility issues by understanding the way we think soil responds to a total stress change. I tried to cram onto a single figure everything the soil mechanics textbooks teaches you about compressibility of clay in particular under a single step loading. So I want you to imagine this is some version of an ergometer. It's drained only at the top, measure water pressure at the base, and put on a total stress increment delta sigma. And we ask what happens. We measure, of course, the strain, and we measure it against time. I happen to plot time on a log scale because the figure is most familiar on the log scale. You will see that on the red, I've got the strain, and on the other axis, I've got the water pressure at the base, which is essentially the center of a two-way draining sample. And you'll see that the water pressure initially is very high. It can be almost the same as the total stress we apply. And with time, the water pressure dissipates. We end up with no water pressure in the system. Everything is total stress is converted to effective stress. That is characteristically occurring at some time frame we say is the time for primary consolidation. We measure strains through that time frame, and we have the strain at the end of primary consolidation, epsilon CF, and then the strains that occur after that, this being the measured result, we say are secondary strains, epsilon S, and then you can see all the analysis and diagnosis of how we get parameters from this. So the primary consolidation we get from the applied load compression ratio of the normal consolidated soil, and you can see the secondary from C alpha and time relative to the end of primary. And we generally are assuming a straight line approximation on a log scale. If you go back to all the literature in soils, you will discover that there's a very interesting relationship between the C alpha, the slope down here, and the CR value we use in primary compression. This was first pointed out by Weisa at University of Illinois. But C alpha to CR is in quite a good correspondence. Many of us use different notations. Some people use C sub C rather than CR, and C alpha E rather than C alpha. The ratio turns out to be more or less the same. In the figures that are about to follow, I'm going to change notation yet again on you. If you see rho alpha to rho C, just think of it as C alpha to C sub C, and it'll all be right. So it's telling you how much we secondary and primary compression we get. We also know the ground rules. Primary compression, we say, occurs because of the fusion of the water pressure and the squeezing of the sponge, essentially the primary compression. Secondary compression is drain and creep, is what we say. What can possibly go wrong? There's a small scaling problem here. Just about all the data you've ever seen are on samples on the left, on a lab sample at the scale of 2 centimeters, and that TP, or TEOP, is less than an hour. You go to Kansai Airport, and the layers of interest are all 10 meters thick, and the time frame of primary is the order of 10 years. And if you do a quick calculation, we would say that's a 6 order of magnitude in time frame scaling, which is a difficult thing to predict. I think we would all agree. This has been known as a problem for a very long time. In fact, the first person who pointed out the scaling problem is in a textbook by a guy called Donald Taylor, who was a professor at MIT in the 1940s. So it's not like it's a new problem. Sometime in the 1970s, it got framed with a certain notation, which I'm going to use. This is from Ladd et al. In 1977. What you can see is the strain versus the log time. So I'm plotting the same thing. The lab test is shown in red here. No funny business, exactly what I just told you. How do you extrapolate this to the field? Well, one approach is to assume that the strain you see here at the end of primary would be the same field scale. So the red is just a translated curve. The red square is translated in time, and that scaling in time is the ratio of the drainage path at field scale squared divided by the square of the drainage path at lab scale. So that point moves here and everything else moves along with it. This drives theoretical people nuts because it upsets them, because they say, how can this be? In the world of creep is a strain-activated process, and time controls how much strain you get. It makes sense to all theoretical people that the longer you have the creep occur, the more creep you get. So, not to put too fine a point on this, people who believe that creep must start to dominate at field scale observe that they would expect to see more strain at this reference time. And they say, well, beyond that, we can all agree. Beyond that, you see the paths converge. We can all agree that creep will occur at a certain rate, and C alpha might be a reasonable parameter. This is not a small difference. So this is what's referred to as hypothesis B. Now, it's, I can't even count, 40-some years since Ladd first defined this, and another 30 since Taylor. What's interesting is we've come this far, and we still don't know why, which one of these would be right. But where we have reached in contemporary soil mechanics is something which is kind of extraordinary. In the measured data, there's contradictory evidence. In other words, the difference in scaling you're seeing here, the A versus B, there are some plays that do one and some plays that do another. That is, I think, fairly definite. If you were to go into a design office or deal with anybody in conventional geotechnical design, the methods, the hand methods we all use, are essentially method A. All people using finite elements are using constitutive models inbuilt into those programs, and they all assume hypothesis B. So we have a fundamental disconnect between the measurements in the lab, the methods used in practice, and the methods that all our numerical modeling friends want us to use in practice. So something's wrong. Let me prove to you, first of all, that in fact there is contradictory evidence, but I think this is rather important. This are two sets of planes, familiar planes. Pisa on the left, and Osaka-Bay clay on the right. And in each case, we're looking at the response to an incremental load. The coloration of the curves, blue is a 2 centimeter thick sample, the conventional size, and red is a 10 centimeter sample. The dotted lines represent the water pressure dissipated as measured, and the solid lines represent the strain. So it's just looking at the same thing we discussed. The time axis is normalized by h squared. You will discover, if you look at the top, that you can't just build a single cell larger and larger and larger, because friction on the side affects the results. So in order to simulate a 10 centimeter thick sample, you have to get quite clever. You will see a hydraulically connected set of 5 cells with water connections. The total stress is applied equally across all the cells. So this is the way to overcome the friction problem. And it's a method that's been used by a number of groups worldwide for 21 years. So the method of getting the 10 centimeter sample is essentially fairly well established at this point. So what do we see? Well, if the 2 and the 10 centimeter samples satisfy hypothesis A, then the strains should follow the same line. And you can see to a first approximation, that's pretty much what happens in Peter clay. If you believe the hypothesis B, there's got to be more strain at the end of the primary, and therefore you would expect to see more strain appearing in the larger sample. That larger sample, much more strain than in this case. And therefore, this is the end of primary, as an approximation. You can see this big offset. So this would be your hypothesis B, if you like. And there's been a lot of work trying to figure out what causes this, where does it come from? And you can look down in the microstructure, and in fact, these two particular materials have such fascinating microstructures. We could probably spend an hour just looking at the micrographs. But they contain microfossils. The one on the right is from Ossipabay. It contains diatoms, which are siliceous. They have all kinds of interesting shapes and occur in abundance. Pretty much all the clays around the Pacific Rim contain lots of diatoms. Very few diatoms, very few fossils in the Pisa clay. What few there are foreign find the algae. So one thought was the microstructure will explain this. We zoom in, we'll find something in the microstructure. Today, all I can tell you is nobody has proved this. In fact, they keep finding examples that contradict this as a hypothesis. So the working hypothesis here doesn't explain it as of today. What can we do about it? Well, it would be nice to have a framework, theoretical framework, that's the coexistence of these two things occur. Because at the moment, we've got people arguing one thing or the other, and they don't acknowledge one another, which is a very bad state of things. In fact, there is a very simple theoretical framework you can put around this, which will capture both. And I just want to illustrate it for you. The idea is contained in this single figure. The idea is that strains, or strain rates, viscoplastic strains, are related to stresses. And RA is a state parameter. RA reflects some sort of state of the material. It's like the mind state, the mental state of our clay, if you like. It's actually an internal strain rate, so a unit of 1 over time, and it's largely 0. We use this parameter as a memory of what has happened to the soil. And the way this memory operates, you can see from the equation here. We say that RA will change when you change the strain rate. So when there's an external stimulus, you will get a response change in RA. That's what we call an activation. Do something externally, it activates. But we damp that. We say that that's related to the current value of RA. That's the decay. So we have a model that activates and decays according to external stimuli, if you like. And the rate of change is conditioned by this parameter MT. We had to go a step further. By the way, if you ask how do things work, you can see this figure showing the internal state variable versus time. They all tend to a steady state value. The rate of change reflects the value of MT. What we discovered is that different materials may actually move their steady state. In other words, certain materials or certain stimuli will cause permanent changes. So we introduced this by putting a variable. The only parameter you need to know here is beta. Beta tells you that the steady state response varies with the stimulus that we put in. If beta is equal to 0, there's no change in steady state. You will revert back to something that the people would call hypothesis A. Beta, if you make beta exactly equal to C alpha over C sub C, or rho alpha over rho sub C, you will essentially get exactly what the current constitutive models assume. In other words, by varying beta or tweaking beta between this range, I can get the two responses that are currently discussed. We could have anything in between. There's nothing stopping constraining beta to be one of those two limits. Let me demonstrate this for you. You're going to see a series of figures. They are essentially looking at stress strain curves. So this is log effective stress void ratio of strain. What you're seeing in this figure is the compression of the soil under constant strain rate. So this is where Weisa comes back into the picture. This is his CRS test driven with a certain rate of strain. And you can see as I vary the strain rate, I vary the position of the consolidation line, the virgin consolidation line. So this is a control rate of strain that I've made beta equal to rho alpha to rho sub C. This is the response that most people in the theoretical community would refer to as an isotope behavior. I can demonstrate this further. Thanks to computer automation and Weisa's equipment, you can step change the strain rate. So you can see the strain rate stepping back and forward, and the red line is the model. The model is moving where the steady state value is, switching back. So you can see the switch back and forward of the steady state according to this change in stimulus. All with this one parameter. So we have captured what the hypothesis speed models do. Now, get rid of the change in steady state. If I compress these all at different strain rates in a steady condition, I get a unique response. But if you look at the step change, you'll realize this is still a time-sensitive material. You will see that I get little blips. Every time I change the strain rate, I get a short-term response, but it goes right back where it came from. So this is where we have no shift in the steady state. And by the way, there are people who have proposed this. There's a fellow in Japan, Tatsuoka, who referred to this as a temporary effect of strain rate. So it's not a unique result, but this is now coming out of the same equations. Take it a step further. Reproducing those lab data of Watabe, comparison of 2 and 20 centimeter thick samples. This is the time plot, the effective stress. You can see if beta is equal to the parameter here, the end of primary is a much larger strain occurring with a larger sample. If I switch beta off, you will see same strain into primary. So shifting the steady state in this formulation is all that's needed to explain the different behavior we're seeing. So now you ask, well, does this work? And this is where things get kind of interesting. So, of course, we proposed this in rather grand. We said, we know what's right here. Why don't you go away and run some tests for us? And so we get these poor guys in Japan to run these tests at 2, 5, 10, 20 centimeter thick samples. And this is what they came back with. This was on another one of the layers of intact material from the Terzaghi. And I think you don't need too much imagination to see there's some contradictory results here. If you look only at 2 and 20, you would declare hypothesis B. If you looked at 5, 10, and 20, you might declare hypothesis A. So something's up, and we could be pretty sure that it's neither one nor the other, which is troubling. We fitted them duly, and of course, just what I told you, you fit them one way or the other, something's going to fall out. So the fitting is not perfect. So the conclusion from this, what can we conclude? Well, maybe we're missing something. Maybe our beta parameter is affected by other things. And we've got some hints at this. We got them to do tests where they changed the strain rate. And then we simply went around curve fitting. We said, well, what beta value would you use? And you can see at certain strain rates, this I think is the fast test. You can see we fit quite well, the model versus the measured, which is in red. And then you see when we go to the slow rate, you'll see we do better with a lower value of beta. In other words, the actual speed of strain likely plays a role. And we didn't really resolve this because, hey, there's going to be something left for you guys to do. But an interesting question is, how could it look? We put the strain rate versus the elapsed time in these tests. And what we're sort of implying to you is that the fast tests, the CRS tests, where beta is at the upper limit, are probably relevant for the small samples. Beta is less than rho alpha to rho C at slower rates. And by the time we reach field consolidation, we may well have beta equal to 0. So all those people in practice may be laughing yet and have proof that hypothesis A was always right all along. So they may be happy. But this seems to me is still a big issue for discussion. So we've put a framework around this. It describes all the behavior, but we still haven't passed where exactly we are on materials. Now, of course, at this point, having made these poor guys do these tests for us, they want to know what's going to happen to this layer in Japan. And the best we can do is say, well, we'll take the two limits and tell you what's going to happen. So this is what we did. And you can see there's their measured data. It was simple. Our prediction is essentially doing A versus B and extrapolating. And I'm not sure I'm going to be here in 2060, but we're forecasting end of primary consolidation in 2060. Someone's laughing, he thinks he's going to be here. But so we've forecasted a very long-term prediction bounded by this model. So it gives us some sense. Now, this is very interesting. It's far away in Japan, affecting an airport in 50 years' time. Less now, 40, 30. We have applied this model in other things. And in order to do it, we have to generalize. I spare you the pretty picture. This is just showing you yield surfaces doing strange things, which we need for shearing. What I want to show you is that the model we've just described affects the way ungrade shear response occurs. And here's an example where we have essentially looked at ungrade shear behavior in clays. This is the stress part. Don't be too alarmed at the look of the stress strain curve. I just drew it on a log scale. It pulls out. Ungrade strength is the peak value. Critical state is this value out here. And what you can see in this figure is us choosing a set of parameters for modeling clay where we see the ungrade strength changing, but this critical state is not changing. And as expected, this is one with a very low beta value. We can repeat this higher beta value, and we shift not just the peak strength, but also the critical state. In other words, critical state is strain rate dependence, which probably wouldn't surprise the people who first worked on this, people like Steve Poulos and Gonzalo Castro. So what I've shown you in A versus B in one-dimensional compression has equal significance when it comes to undrained shear and undrained shear response to clays. And this has been very important for us because we can now tackle really quite complex problems. And for a number of years, we've modeled what happens to the Millennium Tower in San Francisco. If you look at the Millennium Tower, it's a 58-story tower. It's founded on a set of piles which sit on top of a sand layer, coal sand, and then it's sitting above the old bay clay, which is a very deep clay layer, which is very lightly over-consolidated at the start of the 60s. The construction of this tower is immensely complex, because at the same time as building the tower, they built an adjacent garage to it, and then built a podium structure on top of that. So they made a deep excavation next to where the tower is being built concurrently. So we have zones of loading, zones of unloading occurring. So we have a complex change in stressor from the foundation. Not only do we have that, in order to accommodate the construction of the podium, they have to de-water. And therefore they reduce the water pressure in the sand layer. And therefore they provoke consolidation inside the clay associated with reducing the water pressure for a limited period of time. So we have these windows where excavation is occurring, drawdown of water pressures affecting the tower. I haven't here got time, this is a long case study. There are 3 other adjacent structures which also had basements and also drew down water pressures. But what's interesting is this is clearly geared up for our MITSR soil model, because our soil model will let us describe creep and consolidation occurring under all these different conditions. So we can play games. We can ask what are the upper and lower bounds of response we expect to see to this kind of behavior. I probably should have passed over that, but I should point out we do have quite a lot of state data on clay here, and we have enough data to be able to choose parameters for our soil model. I think that's the message I want to be getting across. We then ran these massive predefined element analysis using program Plaxis with our soil model, representing all these complex changes in the old grade clay. We don't have time for all the detail, but what I wanted to try and show you is just a couple of things. First of all, what is the difference between hypothesis A and hypothesis B? The dotted lines are A, solid B. So we're bounding this creep and consolidation interaction in the long term. So if you look at the colored lines and you look at the colored dotted lines and the solid line, you will get the position of sort of the corners of the tower structure over time. And everything is zeroed out here at the end of construction of the tower. So we artificially zero them here, and you can see how you will get settlement, and you'll get differential settlement, and you'll get tilt of the tower in this construction sequence. And you can see how the uncertainty of the creep consolidation often affects this behavior. You can do better than this. You can add in the drawdown. And again, this is color coordinated. I apologize for the excessive detail. Each color is associated with one corner of the tower. Each one has 3 lines. One line, the thin line, says if no one drew down the water pressures, what would happen? The very thick line says this is what happens if you draw down water pressures permanently by about 5 meters. And the dotted line is what happens if you draw down water pressures only during the time frame of construction where you need them and then let them recover. And in each case, you are tracking creep and consolidation as you change, increase, and reduce effective stresses in the soil over time. And you'll see that the transient effect of the drawdown is quite small. It's the order of a centimetre. And you'll see that the permanent drawdown will give you perhaps a drift of 3 or 4 centimetres the most. So we've been able to do studies where we can interpret how the properties of this clay layer affect the settlement versus time and long-term behaviour, and look at all the adjacent structures, which is a future paper. Yes. So where are we at with this piece of work? What I've shown you is that we can capture this viscous behaviour of clays with all their different ramifications through a parameter that depends on the prior strain history, through this internal strain rate parameter RA, which is activated by the strain rate, counterbalanced by decay, and you can see how we can describe transient and steady state behavior. The model unifies all of the observations throughout, all of the contradictory observations. We've generalized it, we've put it into a complete soil model so that we can describe stress strain behavior under general conditions. And we've been able to model, I haven't shown you here, the creep and relaxation you can see in place. It's integrated with finite element codes, and we're already in the business of applying this and seeing how it affects behavior. So in contrast to the tailings dam, we are in forward predictive mode of these complex foundation problems trying to resolve some of these issues of material behavior. Okay, thank you for all your patience. Let me just first of all acknowledge some people here. A lot of former students on the top of this list. I would like first of all to say that the paper I wrote on Fejal failure was co-authored with Hayal El-Nidar and Sherif Apple, both Egyptians. So here we are, the Weisa symposium. We've still got Egyptians at MIT, not only to supervise me, but we're still working. So I'm very happy about this. The rate decay model you saw is in fact largely the PhD work of Yishin Ruan, and then you'll see other people have contributed to the story I told you about. And then I thought specifically I should just thank 4 groups of people. First of all, the finite element limit analysis really has its origin in the work of Scott Sloan, who unfortunately passed away just a few years ago. That's a great loss for our community, and he really was the instigator of this book. The expert panel, which is Peter Robertson chaired the panel, I really think we all owe them a debt because they've released all the data from the failure, which I think is a huge thing. We were very fortunate to work with Yoichi Watabe at the Port Harbour Research Institute. He did a lot of work for us for free, and boy, it was wonderful. He was so helpful to us, we really appreciate it. And finally, the work on Millennium Tower, which I was scratching the surface on, was done in a giant consultative mode as part of litigation, working for Arab, working for Geo-Congress, company of Alan Barr, also a colleague of Anwar. So I'd just like to thank all those people too. And thank you all very much for your patience. Yeah.